Find somewhere comfortable. You don't need to sit up for this or hold anything in your mind. You don't need to remember any of it. If you drift away somewhere in the middle and wake only to the sound of silence, that is perfectly fine. That is, in many ways, the whole point. Tonight we are going to travel somewhere quiet and strange. We are going to go inside the atom, not in any way that asks anything of you, not a lecture, not a test, just a slow walk through one of the most beautiful mysteries in all of science, the mystery of why things fall apart, and why they do it exactly when they do, and not a moment before. It is a question that begins in a darkened drawer in Paris in the winter of 1896. It passes through the heart of matter itself, through forces so powerful they make gravity look faint, and through a randomness so deep that it unsettled the greatest physicist of the 20th century. And it ends, as we will, in something that feels very much like rest. So settle in. Let the weight of the day press you gently into wherever you're lying. The words will come and go. You don't need to catch them. We are in no hurry at all tonight. Paris, in February of 1896, was grey in the particular way that northern European cities become grey in the deep part of winter. Not dramatically dark, but persistently overcast, as though the sky had simply forgotten how to be otherwise. For Henri Becquerel, a physicist at the Museum of Natural History, it was a genuine problem. He had been planning an experiment. A few months earlier, a German physicist named Wilhelm Röntgen had published his discovery of X-rays, invisible rays that could pass through flesh and leave shadows of bone on photographic plates, and the scientific world was quietly electric with the implications. He thought that certain fluorescent minerals, the kind that glow when sunlight falls on them, might also emit these penetrating rays. His plan was simple. He would expose uranium-coated crystals to strong sunlight, then lay them on a wrapped photographic plate, wrapped so that no ordinary light could reach it, and see whether the uranium's fluorescent glow could pass through the wrapping and leave a mark. But the sun would not cooperate. Day after day, the sky remained closed. Becquerel prepared his materials, and then, with the patience of a man who had learned to wait on weather, he placed the wrapped photographic plates in a drawer with the uranium crystals resting on top of them. The clear day did not come. On the 1st of March, after several days of this, Becquerel apparently decided to develop the plates anyway. Perhaps out of curiosity, perhaps out of mild frustration, perhaps simply because he wanted to do something with them before the experiment felt entirely abandoned. What he expected to find was nothing, or at most a very faint shadow, since the uranium had received no sunlight, and therefore, by his hypothesis, should have produced no fluorescent glow and no rays. What he found instead made him look at the plate for a long moment in silence. The image was not faint, it was clear and strong. A ghost shape burned into the emulsion by something that had passed through the wrapping with ease, something that had come from the uranium crystals in total darkness, with no sunlight, no fluorescence, no outside energy source of any kind. He repeated the experiment. He tried it with different wrappings, different distances, different salts of uranium. Every time, the same result. The rays came regardless. They were not caused by light. They were not caused by heat. They were not caused by any chemical reaction he could identify. They emerged steadily and continuously from inside the uranium itself. He had stumbled onto something for which science had no name yet. The energy was coming from within the atom. In that drawer, in that grey Parisian winter, the age of nuclear physics had quietly begun. Becquerel published his findings, and the work was noticed almost immediately by a young Polish-born physicist working in Paris named Marie Sklodowska, who had recently married a French physicist named Pierre Curie. Marie was looking for a subject for her doctoral research, an unusual ambition for a woman at the time, in a world that had not yet decided whether women belonged in laboratories. And Becquerel's mysterious uranium rays caught her attention completely. She and Pierre began working together on the phenomenon, and it was Marie who coined the word that would name it, radioactivity. She used it to describe what she had confirmed was a property of the atom itself, not of molecules, not of chemical bonds, not of any arrangement of atoms, but of the individual atom, something intrinsic and fundamental to certain elements. She discovered something else too, something that would eventually cost her her life. Uranium ore, the raw mineral called pitchblende, was far more radioactive than pure uranium alone. This meant there had to be something else in it, some other element, even more powerfully radioactive, present in tiny quantities. She and Pierre spent years processing tons of pitchblende in a leaking shed in conditions that today would be considered extraordinarily hazardous, and from all that material they eventually isolated two new elements. One they named polonium, after Marie's homeland. The other they named radium, from the Latin word for ray. Radium was remarkable. A small sample of it was measurably warm to the touch, releasing heat continuously with no apparent fuel. It glowed faintly in the dark. It was so intensely radioactive that it could cause radiation burns on skin within minutes of contact. Marie carried small vials of it in her pockets. Her laboratory notebooks are still radioactive today, stored in lead-lined boxes at the Bibliothèque Nationale de France, requiring protective equipment to handle. Meanwhile, a physicist in New Zealand and then Canada and then England, Ernest Rutherford, was pulling at the same threads. He separated radioactive emissions into different types, calling them alpha and beta rays, names that would stick, and began to notice something extraordinary about the atoms that produced them. A uranium atom, after emitting its rays, was not quite uranium anymore. It had become something chemically different, something lighter, something that sat in a different place on the periodic table. Rutherford understood what this meant, and it thrilled him in the way that only truly large ideas can thrill a scientist. Radioactive atoms were transmuting. One element was becoming another. Gold from lead had been the dream of alchemists for 2,000 years. They had filled libraries with their theories and spent fortunes on their furnaces and never come close. And here, in the nucleus of the atom, nature had been doing it all along, quietly, without any furnace, in the dark of every rock and every piece of soil on Earth. Rutherford and his colleague Frederick Soddy published their transmutation theory in 1902 and 1903, and the scientific world received it with a mixture of wonder and, in some quarters, deep skepticism. Elements were supposed to be fixed, eternal, the unchanging building blocks of matter. The idea that they could spontaneously become other elements ran against something almost philosophical in the way scientists thought about matter. But the evidence was unambiguous. The atoms were changing, and no one had yet asked the deepest question: why does a particular atom change at the particular moment it does, and not earlier and not later? That question would take another generation to even begin to answer, and the answer, when it came, was stranger than anyone had imagined. To understand why an atom decays, you have to go inside it. Not just inside the atom, inside the nucleus. That dense, almost impossibly small object at the atom's center, which contains nearly all of its mass in a space roughly 100,000 times smaller than the atom itself. If the atom were the size of a large sports stadium, the nucleus would be a marble sitting at the center of the field, and inside that marble, inside that almost invisible point, there is a drama of competing forces so intense that it makes the rest of physics seem placid. The nucleus is made of two kinds of particles: protons, which carry a positive electrical charge, and neutrons, which carry no charge at all. In a stable nucleus, these particles are packed together with extraordinary density. far denser than anything we encounter in everyday life. A teaspoon of nuclear matter, if you could somehow collect it, would weigh roughly 1 billion tons. Now, here is the first tension at the heart of every nucleus. Protons are positively charged, and positive charges repel each other. This is electromagnetism, the same force that makes a magnet push against another magnet of the same polarity, the same force that stops your hand from passing through a table. In the nucleus, dozens of protons are crammed together at vanishingly small distances, and they are pushing against each other with enormous force. By any electromagnetic reckoning, the nucleus should fly apart immediately. It does not, and the reason it does not is one of the more beautiful facts in physics. There is another force, one that most people never encounter in daily life, because it operates only across distances smaller than the nucleus itself. It is called the strong nuclear force, and it is, within its tiny range, the most powerful force in nature. It grabs protons and neutrons alike. It does not distinguish between them and holds them together with a grip that dwarfs electromagnetic repulsion. At nuclear distances, the strong force wins. The nucleus holds. But the balance is delicate, very delicate. Add too many protons, and the electromagnetic repulsion grows too large for the strong force to overcome across the whole nucleus. Add too many neutrons, and a different problem emerges. The neutrons themselves begin to interact with the weak nuclear force, a third fundamental force responsible for certain kinds of particle transformations, and the nucleus becomes unstable in a different way. There is, for every element, a range of neutron to proton ratios that keeps things stable, and outside that range, the nucleus begins to feel a kind of pressure, a tendency toward rearrangement, toward a lower energy configuration. Physicists sometimes describe this using the image of a landscape, an energy landscape, a kind of topography of nuclear configurations. In this imaginary landscape, stable nuclei sit in the valley floor, the lowest possible energy for their particular combination of protons and neutrons. Unstable nuclei perch on the slopes. And things on slopes, in physics as in life, tend to roll downward. Carbon is a useful example to hold in mind. Carbon-12, the most common form of carbon, the carbon in your body, in wood, in every organic molecule, has 6 protons and 6 neutrons. This combination sits beautifully in the valley. It is profoundly stable. Carbon-12 does not decay. It has existed as carbon-12 since the first stars forged it in their cores billions of years ago, and it will continue to exist as carbon-12 for as long as the universe persists. Carbon-14 is different. It has the same 6 protons. It is still carbon, chemically indistinguishable from carbon-12, but it has 8 neutrons instead of 6. Those 2 extra neutrons push it just far enough up the slope of the energy landscape that it is no longer comfortable where it is. It is unstable. Not dramatically, not in a way that would cause it to explode or glow, just quietly, persistently unstable in the way that something perched slightly wrong on a surface is unstable. Given time, it will shift. It is worth pausing on what unstable means here, because it does not mean fragile in any ordinary sense. A single atom of carbon-14 can sit unchanged for thousands of years. Its instability is not urgency. It is more like potential, a stored tendency toward change that may or may not express itself at any given moment. The nucleus does not know it is unstable. It does not experience the passage of time. It simply exists in a configuration that is not the lowest possible energy. And at some point, in a way that quantum mechanics governs but does not predict, it will find its way to something more settled. The number of stable isotopes, forms of elements with stable nuclei, is surprisingly limited. There are roughly 250 of them among all the elements. Everything else, all the other combinations of protons and neutrons that can be assembled, is radioactive to some degree. Some are so unstable They exist for only fractions of a second before transforming. Others, like carbon-14, persist for thousands of years. Others, like certain isotopes of uranium and thorium, persist for billions. What determines how long an unstable nucleus persists before it decays is connected to how far up the slope it sits, how large the gap is between its current energy and the lower energy configuration it is trying to reach. A nucleus that is very far from stability tends to decay quickly. One that is only slightly off the valley floor may take an enormous time to find its way down. But even this is not quite right, because the timing of any individual decay event is not determined by the size of the energy gap alone. There is something else going on, something that sits at the heart of quantum mechanics and that no classical picture of the nucleus can explain. Even a nucleus with a very well-characterized energy gap, one that we understand in great detail, will decay at a moment that cannot be predicted in advance by any measurement or calculation. The randomness is not in our ignorance. It is in the nature of the thing itself. That is the deeper mystery, and we will arrive at it properly in a little while. For now, it is enough to hold the image, a nucleus perched on a slope, surrounded by forces that both hold it together and press against it, waiting, without knowing it is waiting. The heavy elements, the ones with the most protons, feel this tension most acutely. Uranium has 92 protons. The electromagnetic repulsion among 92 positive charges, all crammed into a space the size of a nucleus, is immense. The strong force still holds the nucleus together. Uranium nuclei exist in a state of perpetual, barely managed tension, and eventually, every one of them will find a way to release it. There is something almost restful in that image if you let it settle. The tension held and held and held, and then, at last, released. When a nucleus finally moves toward that lower energy configuration, it does not always do so in the same way. Nature has three principal methods, and each has its own character, its own texture, its own scale of violence and quiet. The first is called alpha decay, and it is in some ways the most visually satisfying to imagine. A heavy nucleus, uranium, thorium, radium, one of the large and crowded ones, spontaneously ejects a tightly bound cluster of 4 particles, 2 protons and 2 neutrons, locked together in a configuration that is itself extraordinarily stable. This cluster is, in fact, identical to the nucleus of a helium atom. 2 protons, 2 neutrons, bound so tightly together that they move as a single unit. The ejected cluster flies away from the nucleus at speeds of roughly 15,000 kilometers per second, about 5% of the speed of light, carrying with it a significant chunk of the nucleus's energy. The original nucleus, now missing 2 protons and 2 neutrons, has become a different element. Uranium-238, with 92 protons, loses 2 protons and becomes thorium-234 with 90 protons. The atom has changed. The element has changed. Alchemy accomplished in a moment. The reason a nucleus sheds specifically this 2+2 cluster, rather than some other combination, is that this particular grouping is extraordinarily stable, so stable that it forms naturally inside the nucleus, like a substructure within the larger structure, and it is this preformed unit that gets ejected. The strong force binds it so tightly that it holds together as a coherent object even as it separates from the parent nucleus. Alpha particles, as these ejected helium nuclei are called, are relatively massive and carry a double positive charge, which means they interact strongly with whatever matter they pass through. They are stopped almost immediately by a few centimeters of air, by a sheet of paper, by the outer layer of human skin. They do not travel far. But inside a living cell, if an alpha emitter is somehow ingested or inhaled, the damage they cause is severe precisely because all their energy is deposited in a very small volume of tissue. Beta decay is more subtle and in many ways more philosophically interesting. It comes in two forms, and the first, the one Becquerel and the Curies were detecting in their early experiments, though they did not yet know its nature, involves a transformation inside the nucleus that has no analogy in everyday chemistry. A neutron, sitting inside the nucleus, converts into a proton, not collides with something, not breaks apart in any simple mechanical sense, converts, changing its fundamental character. In doing so, it releases two particles, an electron, which flies out of the nucleus at high speed, and a nearly massless particle called an antineutrino. The antineutrino is almost a ghost. It interacts with ordinary matter so weakly that it can pass through the entire Earth as though the Earth were not there. Billions of antineutrinos pass through your body every second from various sources without any of them ever touching a single atom of you. The force responsible for this neutron-to-proton conversion is the weak nuclear force, the same fundamental force that is responsible for the nuclear fusion reactions powering the Sun. It is called weak, not because it is feeble in any absolute sense, but because it operates across an extraordinarily short range, even shorter than the strong force, and its effects are correspondingly subtle. When the weak force acts on a neutron inside a nucleus, it can trigger this conversion, and the nucleus finds itself with one more proton and one fewer neutron than it had before. This means the element changes. The atomic number increases by 1, while the total number of protons and neutrons stays the same. Beta minus decay, as this process is called, tends to occur in nuclei that have too many neutrons relative to their protons. The conversion of a neutron to a proton nudges the nucleus back toward a better balance. There is also a mirror version called beta plus decay, in which a proton converts into a neutron, releasing a positron, the antimatter counterpart of the electron, identical in mass but carrying a positive charge, along with a neutrino. Beta plus decay tends to occur in nuclei that have too many protons relative to their neutrons. The proton becomes a neutron, the balance improves, and the nucleus edges closer to the valley floor. Positrons are interesting objects. When a positron encounters an ordinary electron, which happens almost immediately, since electrons are everywhere in matter, the two annihilate each other completely, converting their combined mass into two photons of gamma radiation, flying off in opposite directions. This annihilation is the basis of PET scanning, positron emission tomography, the medical imaging technique that allows doctors to see metabolic activity inside the body. The body's own radioactive tracers, decaying by beta plus, reveal where glucose is being consumed most actively: in tumors, in regions of heightened brain activity, in inflamed tissue. Gamma decay is the quietest of the three, and in some ways the most elegant. No particles leave the nucleus. Nothing is ejected. The nucleus simply releases energy in the form of a pulse of electromagnetic radiation, a photon of very high frequency, far higher than visible light, far higher even than X-rays. This photon carries away the excess energy that was keeping the nucleus in an agitated, elevated energy state, and the nucleus settles into a calmer configuration. The element does not change during gamma decay. The number of protons is the same before and after. The number of neutrons is the same. What changes is only the internal energy of the nucleus. It steps down from an excited state to a lower one, releasing the difference as a gamma ray. Gamma rays are extraordinarily penetrating. Where alpha particles are stopped by paper and beta particles by a few millimeters of aluminium, gamma rays require centimeters of lead or meters of concrete to be substantially absorbed. They pass through flesh with ease, which is what makes them useful in cancer radiotherapy. They can be aimed at a tumor from outside the body, and what makes them hazardous in uncontrolled exposures. It is worth holding these three modes together for a moment, as a kind of quiet inventory. Alpha decay. The nucleus sheds mass, ejects a heavy cluster, and becomes a lighter element. Beta decay. A particle inside the nucleus changes identity. The element shifts by one step on the periodic table, and a nearly invisible particle escapes into the universe. Gamma decay. No change in composition, just a release of energy, a nucleus breathing out its tension in a pulse of light. 3 ways of settling, 3 ways of moving, in the language of that energy landscape, from the slope toward the valley. Each one leaves the nucleus in a state slightly closer to stability, and often it takes not one decay but a whole sequence of them, a chain of transformations stretching across the periodic table, before a nucleus finally arrives at a configuration that is truly at rest. The patience involved in this process is something we will come back to. It is one of the things about radioactive decay that, if you let it, can feel almost companionable in the dark. And now we arrive at the question that sits at the center of all of this, the question that is in some ways the strangest fact in science. Why does a particular atom decay at the precise moment it does? Not why does it decay at all. We have been building toward that. The energy landscape, the competing forces, the imbalance of protons and neutrons, all of that explains why a given nucleus is unstable, why it will eventually change. But it says nothing about when. Nothing about why this atom, in this sample, decays at this particular instant, while its neighbor, chemically identical, physically identical, subject to the same forces in the same environment, persists for another 10,000 years. The honest answer is that no one knows. And more than that, it is not the kind of not knowing that more research will eventually resolve. It is a fundamental feature of how nature works at this scale. To understand why, you have to step into quantum mechanics, the framework that describes how the very small behaves, and which consistently produces results that feel deeply strange when you try to translate them into the language of everyday experience. In quantum mechanics, a particle does not have a single definite position, or a single definite energy, or a single definite future. Instead, it exists in what physicists call a superposition, a kind of smeared distribution of possibilities, each with a certain probability. The particle is not in one place waiting to be found. It genuinely occupies a range of possible states simultaneously, and only when something interacts with it, when it is measured, or when it interacts with another particle, does this smear of possibility resolve into a single outcome. This is not a limitation of our measuring tools. It is not that the particle has a definite position and we simply cannot see it precisely enough. The wave-like spread of possibilities is real. It is the actual state of the particle. The definiteness comes later, at the moment of interaction. Now, apply this to a nucleus. Inside a heavy nucleus, consider the alpha particle, that cluster of 2 protons and 2 neutrons. That is going to be emitted eventually. In classical physics, the kind of physics that works perfectly well for billiard balls and planets, the alpha particle will be trapped inside the nucleus by an energy barrier. It simply does not have enough energy to climb over the wall of the strong force holding it in. By any classical reckoning, it should stay inside forever. But it does not stay inside forever, and the reason involves one of the most striking consequences of quantum mechanics, a phenomenon called quantum tunneling. Here is how to think about it. Because the alpha particle exists in a quantum smear of probabilities, its position is not precisely defined. There is a small but non-zero probability that, at any given moment, the alpha particle is located outside the barrier rather than inside it. Not that it climbed over the barrier, or that the barrier temporarily weakened, but that the particle's quantum nature means it can be found on the other side without having traversed the space in between in any classical sense. The barrier is not quite solid because at this scale, nothing is quite solid in the way we mean when we say solid. When this happens, when the alpha particle is found, so to speak, on the outside, the nucleus has decayed. The alpha particle is gone. The decay has occurred. And this process, this quantum tunneling, is intrinsically probabilistic. There is no hidden mechanism inside the nucleus counting down to a predetermined moment. There is no internal clock. The probability of tunneling is constant over time. The nucleus does not become more or less likely to decay as time passes. Each moment is as likely as any other. The decay happens when, by the irreducible randomness of quantum probability, the alpha particle finds itself outside. This is what Geiger counters are measuring. A Geiger counter, the device that makes that familiar irregular clicking sound in the presence of radioactive material, detects individual decay events. Each click is a single nucleus releasing its energy. More. And if you listen to a Geiger counter in the presence of a radioactive sample, you will notice that the clicks do not come at regular intervals. They are scattered, two close together, then a gap, then another, then a cluster, then silence. The pattern is random, not pseudo-random, not complex, but deterministic, but genuinely, irreducibly random. No algorithm could predict when the next click will come. This randomness disturbed Albert Einstein profoundly. He famously resisted it for decades, feeling that a universe governed by genuine chance at its foundations was philosophically unacceptable. His objection was captured in the phrase he used repeatedly in arguments with Niels Bohr, that he could not believe God played dice with the universe. He felt deeply and persistently that the randomness was an appearance, that beneath the quantum smear there must be some deeper layer of reality, some hidden variables, some more complete description of the particle that would, if known, allow the decay to be predicted. The debate between Einstein and Bohr was one of the great intellectual exchanges of the 20th century, conducted over decades through letters and conferences and published papers. It was not merely a technical disagreement. It was a disagreement about the nature of reality itself, about whether the universe, at its deepest level, is deterministic, or whether chance is genuinely woven into the fabric of things. The experimental evidence, accumulated over decades since Einstein's death, has consistently favored Bohr's view. In the 1960s, a physicist named John Bell devised a mathematical test, a way of distinguishing between a quantum randomness that is truly fundamental and one that merely conceals hidden deterministic variables, and subsequent experiments have confirmed with remarkable precision that the randomness is real. The nucleus genuinely does not know when it will decay. The universe, at this scale, is not playing a game whose outcome is predetermined. It is genuinely, irreducibly open. There is something in this that, if you let it, can feel unexpectedly freeing. The future of a single atom is not written anywhere. It is not determined. It will happen when it happens, and until that moment, the possibility simply exists, patient, open, waiting. The Geiger counter clicks in the dark, irregular, unhurried, each click the resolution of a probability that had been accumulating since the nucleus formed, each one unrepeatable, unrepeated, arriving in its own time. And yet, from all this irreducible randomness, something extraordinarily orderly emerges. Take a large collection of identical radioactive atoms, say 1 billion atoms of carbon-14. You cannot predict when any single one of them will decay. You cannot look at one atom and say, this one will go in the next hour, that one will last another 1,000 years. They are indistinguishable, and their futures are genuinely open. But watch the whole collection, measure the total number of decays happening each second, and you will find something remarkable. The rate at which the collection shrinks is perfectly, precisely, mathematically predictable. Not approximately predictable. Precisely. Precisely. The randomness of the individual is absorbed, at scale, into an elegant regularity. This regularity is expressed through the concept of half-life, a term coined by Ernest Rutherford around 1907, though the underlying mathematics had been taking shape for a few years before that. The half-life of a radioactive isotope is the time it takes for exactly half of any given quantity of that isotope to decay. It does not matter whether you start with 1 billion atoms or 1 trillion. It does not matter whether the sample is hot or cold, compressed or expanded, dissolved in acid or embedded in rock. After one half-life, half remain. After 2 half-lives, 1/4. After 3, 1/8. The proportion is always the same, and the timing is always the same. This is because each atom decays independently with its own fixed probability per unit of time, and when you have vast numbers of independent random events, each with the same probability, the mathematics of statistics produces an outcome of extraordinary smoothness and regularity. It is the same reason that, although you cannot predict any single flip of a coin, you can predict with great confidence that 1 million flips will produce very close to 500,000 heads. An image that might help. Imagine a vast crowd of people, each standing alone in a field, each flipping their own coin at their own pace, each following their own rhythm. No two of them are synchronized. No one is watching anyone else. Each person flips whenever they feel like it, and when they get tails, they sit down. From any individual, you can predict nothing, but looking at the crowd as a whole, you can say with confidence, in the time it takes for the average person to flip their coin once, roughly half the crowd will have sat down. The individual is random. The crowd is a clock. The half-lives found in nature span a range that is almost impossible to hold in the mind all at once. At one extreme, there are isotopes so unstable that their half-lives are measured in microseconds, millionths of a second, or even shorter. These are the highly exotic, far from stability nuclei that physicists create in particle accelerators, and they exist for barely an instant before transforming. At the other extreme, there is uranium-238, whose half-life is 4.5 billion years. 4.5 billion years. Uranium-238 was forged in the violent death of a star before our solar system existed. It drifted through space as part of the cloud that eventually collapsed to form the Sun and its planets. And it has been decaying. Slowly, ever since, so slowly that roughly half of the original atoms are still here, still uranium-238, still waiting for their moment. The other half have already made their journey step by step through a chain of intermediate elements towards something more stable. That journey, the decay chain of uranium, is one of the more patient stories in nature. Uranium-238 decays by alpha emission into thorium-234. Thorium-234 decays by beta emission into protactinium-234. Protactinium-234 decays into uranium-234. Protactinium-234 decays into uranium. And so it continues, through more than a dozen intermediate steps, each one a nucleus, finding a slightly lower energy configuration, each one releasing a small pulse of energy into the surrounding rock. The chain passes through radium, the element Marie Curie isolated from tons of pitchblende, and through radon, a gas that seeps up through soil and can accumulate in basements and eventually arrives at lead-206, which is stable. The journey is complete. The nucleus has found the valley floor. The intermediate isotopes in this chain have half-lives ranging from fractions of a second to tens of thousands of years. Each step is its own patient process, its own statistical clock ticking away in the dark of the earth. It is worth pausing on the sheer span of these numbers because they open a kind of vertigo that is, in the right frame of mind, deeply restful. Polonium-214, one of the intermediates in the uranium decay chain, has a half-life of about 164 microseconds. In the time it takes you to blink, A sample of polonium-214 has gone through millions of half-lives, reduced to an almost immeasurably small fraction of its original amount. Meanwhile, in the same rock, the uranium-238 from which it ultimately descended has barely noticed the passage of a human lifetime. Its half-life is so vast that the entire history of human civilization represents less than 0.001% of it. These two timescales exist simultaneously in the same mineral, in the same piece of granite, the fleeting and the ancient side by side, each operating on its own rhythm, each indifferent to the other. Rutherford understood the power of this. If you know the half-life of an isotope and you can measure the ratio of parent atoms to daughter atoms in a sample, you can calculate how long the decay has been proceeding. You can date the sample. The radioactive clock, once set, runs without interruption, unaffected by anything the physical world can throw at it. Temperature, pressure, chemistry. None of these change the half-life. The clock runs in the deep cold of space and in the heat of the Earth's mantle, and it runs at exactly the same rate in both places. This is the foundation of radiometric dating, one of science's most powerful tools for reading the past, and the story of how that tool was built and what it revealed is one worth following a little further. In the late 1940s, a chemist at the University of Chicago named Willard Libby was thinking about carbon. Specifically, he was thinking about carbon-14, that slightly heavy, slightly unstable isotope with its 2 extra neutrons. And a question that had occurred to him: if carbon-14 is constantly being produced in the atmosphere and constantly decaying and living things are constantly absorbing it, then the moment an organism dies should be readable in its atoms. The mechanism is elegant. High in the upper atmosphere, cosmic rays, energetic particles streaming in from space, collide with nitrogen atoms. When a cosmic ray strikes a nitrogen nucleus just right, it can knock out a proton and replace it with a neutron, transforming nitrogen-14 into carbon-14 into carbon-14. This happens continuously all over the Earth, and the carbon-14 produced in this way quickly joins with oxygen to form carbon dioxide, which circulates through the atmosphere and is absorbed by plants during photosynthesis. Animals eat the plants. The carbon-14 works its way into every living organism, maintaining a roughly constant ratio to ordinary carbon-12. While the organism is alive, this ratio stays stable. Carbon-14 is being absorbed as fast as it decays, but the moment the organism dies, the moment a tree is felled, a shell closes for the last time, an animal takes its last breath, the absorption stops. Carbon-14 continues to decay, converting back into nitrogen-14 with its half-life of 5,730 years, and the proportion of carbon-14 to carbon-12 in the remains falls steadily, measurably, predictably. Measure the ratio in a sample today, compare it to the ratio you would expect in a living organism, and the mathematics of half-life tells you how long ago the organism died, how long the clock has been running. Libby tested his method on samples of known age, wood from Egyptian tombs whose dates were established by historical records, for instance, and the results were striking. The carbon-14 measurements agreed with the historical dates to within the margin of error. The atomic clock was running true. Libby received the Nobel Prize in Chemistry in 1960 for this work, which had by then transformed archaeology, anthropology, and the study of ancient climate. The applications accumulated quickly. The Dead Sea Scrolls, discovered in caves near Qumran beginning in 1947, were dated by radiocarbon analysis to the period between roughly 250 years before the Common Era and 70 years into it, consistent with the historical context suggested by their content and confirming that they were genuinely ancient documents rather than later copies. The Shroud of Turin, a length of linen bearing the image of a man, long venerated as the burial cloth of Jesus, was tested in 1988 by 3 independent laboratories using radiocarbon dating. all three arrived at the same conclusion. The flax from which the linen was woven was harvested somewhere between 1200 and 1300 years into the Common Era, placing the cloth in the medieval period. The dating was precise enough to suggest the fibers dated to between roughly 1260 and 1390, consistent with the first documented appearance of the shroud in historical records in France in the 1350s. Wooden beams from Egyptian tombs, animal bones from ancient settlements, charcoal from prehistoric hearths, seeds found in archaeological layers, all of these carry their carbon-14 clocks inside them, ticking since the moment of death, waiting to be read. But carbon-14 has a limit. Its half-life of 5,730 years means that after about 60,000 years, the remaining carbon-14 in a sample is too small to measure reliably. The signal fades into the noise. For anything older than that, for the deep geological past, for the age of rocks and mountains and the Earth itself, a different clock is needed, one with a much longer half-life. Uranium-lead dating fills this role. Uranium-238 decays through its long chain of intermediates and eventually becomes lead-236. Uranium-235, a slightly lighter isotope, decays along a different chain and becomes lead-237. The technique works by measuring the ratio of uranium to lead in a mineral crystal, particularly a mineral called zircon, which incorporates uranium into its structure when it forms but actively excludes lead. This means that any lead found in an ancient zircon crystal must have accumulated since the crystal formed through radioactive decay. The ratio of uranium to lead is therefore a direct measure of the crystal's age. Zircon crystals from ancient rocks in Western Australia, from a formation called the Jack Hills, have been dated by this method to 4.4 billion years old. They are the oldest material yet found on Earth, fragments of the planet's original crust that somehow survived the violent early period when impacts and volcanic activity reshaped the surface repeatedly. They are, in a very real sense, pieces of the newborn Earth. Meteorites, fragments of rock that formed in the early solar system and have drifted in space ever since, occasionally falling to Earth, have been dated using uranium-lead methods to 4.5 to 4.6 billion years old. This measurement, repeated on multiple meteorites from different origins, converged on a consistent answer. The solar system formed approximately 4.5 billion years ago. There is something quietly extraordinary about this. The same physics that Henri Becquerel stumbled upon in that grey Parisian winter, the same emissions that fogged his photographic plate in a dark drawer, turned out to be the key to reading the deepest history of the planet. The same randomness that makes each individual decay unpredictable became, at scale, a clock of almost unimaginable precision, capable of measuring time across 4 billion years. The atoms were keeping records all along. We simply learned to read them. Radioactive decay is not only a laboratory phenomenon, not only a tool for dating the past. It is a force actively shaping the present, shaping the planet you are lying on right now, shaping the cosmos you are embedded within. Beneath your feet, below the soil and the bedrock, below the continental crust and the deep mantle, the Earth is hot, extraordinarily hot. At the boundary between the mantle and the outer core, temperatures reach 4,000 degrees Celsius. At the very center of the Earth, the pressure is so immense and the temperature so high that the iron there exists in a state unlike anything we can recreate in a laboratory. Where does all this heat come from? Some of it is primordial, the residual warmth from the formation of the planet itself, when billions of years of colliding rock and gravitational compression generated heat that has been leaking outward ever since. But primordial heat alone would not be sufficient to keep the Earth as hot as it is for as long as it has been. The planet should, by that account alone, have cooled significantly more than it has. The missing heat, comes from radioactive decay. Deep in the mantle and the crust, uranium, thorium, and a radioactive form of potassium, potassium-40, which decays by both beta emission and electron capture into argon-40 and calcium-40, are releasing energy continuously as they have been doing since the Earth formed. Each decay event releases a small pulse of energy which is absorbed by the surrounding rock and manifests as heat. Individually, these pulses are tiny. Collectively, across the vast volume of the Earth's interior, they contribute roughly half of the total heat flowing out of the planet. This heat does things. It keeps the lower mantle warm enough to flow very slowly over geological timescales, and this flowing mantle is what drives the movement of tectonic plates. The continents drift, mountains rise, ocean floors spread apart, earthquakes shake the surface. All of this is, at its root, driven in part by the heat of radioactive decay in the deep earth. The volcanoes that built the Hawaiian Islands, the rift that is slowly pulling East Africa apart, the subduction zones where one plate slides beneath another and generates the deep earthquakes of the Pacific Ring of Fire, all connected through the long chain of geological consequence to atoms decaying in the dark interior. The liquid outer core is particularly important. Iron in the outer core is kept liquid by the heat flowing from deeper within, and this liquid iron, circulating in complex patterns, generates the Earth's magnetic field through a process similar to the way a dynamo generates electricity. The magnetic field extends tens of thousands of kilometers into space, deflecting the charged particles of the solar wind that would otherwise erode the atmosphere and bombard the surface with radiation. Without the magnetic field, life on Earth's surface would face a very different radiation environment. Without the liquid outer core, there would be no magnetic field. Without the heat of radioactive decay, the outer core might long ago have solidified. The warmth of the Earth, the drift of the continents, the shield of the magnetic field, the existence of conditions hospitable to life, all of these trace back, in part, to the patient, invisible decay of atoms deep below the surface. Now travel outward, far outward. In 1977, 2 spacecraft were launched from Cape Canaveral, Voyager 1 and Voyager 2, on a journey that was intended to last perhaps 4 or 5 years, long enough to visit Jupiter and Saturn. They have now been traveling for nearly half a century. Voyager 1, as of the time this is being written, is more than 23 billion kilometers from the Sun, farther from the Sun than any human-made object in history, drifting through interstellar space, the space between stars. Both spacecraft are still transmitting. Their instruments are still recording. Their signals still reach Earth after a journey of more than 22 hours at the speed of light. They are powered by radioactive decay. Each Voyager carries a set of devices called radioisotope thermoelectric generators, RTGs in the shorthand. Inside each generator is a quantity of plutonium-238, a radioactive isotope with a half-life of 87.7 years. Plutonium-238 decays by alpha emission, releasing heat continuously. That heat is converted directly into electricity by thermocouples, devices that produce a voltage when one side is hotter than the other. No moving parts, no fuel to be replenished, no engine to maintain, just the steady, patient decay of plutonium atoms, releasing energy in the cold dark of the outer solar system. When Voyager 1 was launched, each RTG produced roughly 470 watts of electricity. Decades later, the power has declined as the plutonium decays, following its half-life faithfully. But enough remains to keep the essential instruments running. The spacecraft that left Earth before many of the people listening to this were born is still alive, still measuring the properties of interstellar space, powered by nothing more than atoms following their nature. And then there are the stars. A Type Ia supernova is a particular kind of stellar explosion, one that occurs in a binary star system. when one star has become a dense, collapsed object called a white dwarf and is drawing material from its companion. When enough mass accumulates on the white dwarf's surface, a runaway nuclear fusion reaction ignites, and the entire star is destroyed in a matter of seconds, briefly outshining its entire galaxy. These explosions are important to cosmologists because they all explode with roughly the same intrinsic brightness. This makes them useful as what astronomers call standard candles, objects of known luminosity that can be used to measure distances across the universe. The discovery that the universe's expansion is accelerating, one of the most significant astronomical findings of the late 20th century, relied on observations of type Ia supernovae. What powers the light of a type Ia supernova after the initial explosion? The explosion itself lasts only seconds, but the light curve, the way the brightness rises and then fades over weeks, is shaped by radioactive decay. The explosion synthesizes large quantities of nickel-56, a radioactive isotope that decays by beta plus emission into cobalt-56 with a half-life of about 6 days. Cobalt-56 then decays into stable iron-56 with a half-life of about 77 days. The energy released by these two sequential decays, absorbed and re-emitted by the expanding gas cloud of the explosion, is what makes the supernova visible across billions of light-years of space. The brightness of a dead star, measured by a telescope on Earth, follows a curve shaped by the half-lives of nickel and cobalt. The light you see, or rather, the light that astronomers photograph, is the energy of radioactive decay, released in the heart of an explosion, carried across the universe, arriving at a detector after a journey of billions of years. A half-life written across the sky. We have come a long way tonight. From a dark drawer in Paris, from the grey winter light that never came, we have descended into the nucleus. That dense, tense, almost incomprehensibly small world where protons and neutrons press against each other under forces that dwarf anything in ordinary experience. We have watched atoms shed their excess in 3 different ways, each one a small step toward a lower, stiller configuration. We have sat with the deep strangeness of quantum randomness, the fact that no one can predict when a single atom will let go, and that this unpredictability is not a failure of knowledge, but a feature of reality itself. And from all that randomness, we have watched something beautiful emerge. The half-life, reliable and unchanging, a statistical clock so precise that it can read the age of the oldest rocks on Earth, date the wood of an ancient tomb, measure the distance to a dying star. If you are still awake, let what follows arrive softly, and if you are already drifting, that is entirely fine. These last words are not meant to be held. They are meant to accompany you on the way down. There is something about the scale of radioactive decay, the way it operates simultaneously across microseconds and across billions of years, that has always felt, to those who sit with it long enough, like a kind of perspective. Not the kind that diminishes, that makes you feel small in an uncomfortable way. The kind that reminds you that the universe is conducting its business on timescales so vast that whatever you are carrying tonight, whatever weight came through the door with you, whatever the day did or did not give you, is held within something almost unimaginably patient. Uranium-238 has been waiting since before the Earth existed. Most of its atoms are still waiting. They do not experience the wait. They do not grow tired of it, or anxious about it, or impatient with it. They simply exist in their configuration, subject to the quiet probability of quantum mechanics until the moment arrives. And then, without urgency, without drama, they let go. There is a parallel here that does not need to be forced. Rest works something like this. You cannot decide to fall asleep the way you decide to stand up or open a door. You can create the conditions, the darkness, the stillness, the warmth. But the actual crossing from waking into sleep is not something you do. It is something that happens to you when the conditions are right, when the probability tips over. The brain, in moving towards sleep, passes through its own sequence of energy states. While you are awake, it hums with what are called beta waves, electrical rhythms oscillating many times per second, associated with active thought, with the processing of sensation and language in memory. As you relax, these give way to alpha waves, slower, around 8 to 12 cycles per second, the rhythm of a mind that is still present but no longer straining. Drifting further, theta waves emerge. 4 to 8 cycles per second, the rhythm of the threshold, the place where thoughts become untethered and images arrive unbidden. And in the deepest sleep, the slow delta waves take over. Half a cycle per second, or perhaps 1 or 2. The slowest electrical rhythm the brain produces in health. During delta sleep, the brain is not inactive. It is doing some of its most important work, consolidating memories, releasing growth hormone, repairing the body's tissues, clearing the metabolic byproducts that accumulate during waking. But it is doing this work quietly, without the noise of conscious thought, in a lower energy state, a stiller configuration. Like a nucleus that has found its way to the valley floor. The day you have lived through, whatever it held, however much it asked of you, has left its traces in your nervous system, in the tension of your muscles, in the chemical state of your brain. Sleep is how those traces are processed and released. Not forced out, not controlled, but allowed to settle. The way a disturbed pool of water eventually returns to stillness when nothing is adding to the disturbance. The atoms in the rock beneath you are decaying, slowly, releasing their energy into the warmth of the earth. The Voyager probes are drifting through the dark between stars, powered by the quiet decay of plutonium, still sending their faint signals home. Somewhere in the sky, the light from a supernova that exploded billions of years ago is still traveling, its brightness shaped by the half-lives of atoms forged in the heart of that explosion. All of this is happening right now while you lie still. The universe is conducting its vast, patient business, and it asks nothing of you tonight, nothing at all. The carbon-14 in your body, the small fraction of your carbon that is the unstable, slightly heavy kind, is decaying atom by atom at its own unhurried pace. You will never notice it. It is quieter than a whisper, quieter than a breath. And it has been happening since before you were born, and it will continue after everything you know has changed. Each decay is its own small release, its own small step toward equilibrium. You, too, are moving toward equilibrium tonight. The body knows how to do this. It has been doing it every night of your life, through every difficulty and every exhaustion, finding its way back to the deep, slow rhythm of rest. You do not need to help it. You only need to let it. The questions of the day can wait. The things undone, the things said or unsaid, the things that feel unresolved. They will still be there tomorrow, and you will be better equipped to meet them after your brain has had its time in the slow delta dark. Tonight, they can be set down. The nucleus does not know when it will decay. It does not plan for it, or worry about it, or count the moments. It simply exists, patient and open, until the moment arrives in its own time. You do not need to know when sleep will come. It will come. It always does. And so we leave it there. Somewhere behind you, the day is already growing distant. Let it drift further. The universe is very old and very patient, and tonight it is keeping watch. Sleep well.